Okay, good morning, everyone. Let's start the next section of my lecture series on Geology of Sri Lanka. Actually, I think you have already have kind of the background knowledge about the tectonic units of Sri Lanka, right? The complexes, tectonic complexes. So, uh, Highland complex, Vijayan complex, Vani complex, and Kaduganav complex. Those are the main tectonic units we have, and we discussed about their petrology and some other information, including PT conditions, the metamorphic grades, etc. I think I ask you to refer the book, the paper by Kure, 1994. That is the main paper that we use for this classification, and you must know about that, and you must have read that paper by now, because it's not a very complicated paper, and you can easily understand it now. And even after your graduation, you must be knowing very well about that paper, because that is a very descriptive paper about the geology of Sri Lanka. So if you don't know about that paper, and also about the knowledge, I mean the content given in that paper, you'll be having some problems when you are going to do the job in geological fields, wherever you will join as a geologist, or even if you are going for higher studies. Okay, and the other thing is the Crystalline Crust of Sri Lanka book. I ask you to photocopy from the science library. So please do that also. It contains all the aspects of geological uh, research work done mainly during the 1990s time. That is the peak of the Sri Lankan geological research. Okay, we are now moving to the geochronology part, and this part is also included in the said papers and the book. So please make sure you understand them. You might not be able to understand all the geochronological papers and the facts given there, but you will have a basic knowledge here. And at your final year, if you are selected, at the final year, you will be getting more details of this isotopic studies, geology, and the principles. But this concept you must know, irrespective of you are honor student or a general student. Okay, so we'll mainly consider about the isotopic studies on Sri Lankan rocks. So you know the isotopes which are having radiogenic isotopes. Actually, I think by at your A levels, you know in chemistry what are the isotopes. Isotopes are having extra extra neutron in the nucleus. So you will have a different mass, so that it is showing some different chemical properties. So these isotopes are produced as a result of radiogenic decay, right? You know that. You know the half life. That means the time duration to convert parent element to produce daughter elements. Uh, that means the abundance or the amount available at the initial time, say it's 100%, and then the time taken to make it 50% at a later time, to make 50%, the time taken is considered is called half-life. Okay, so that is the basic principle of radiogenic isotope decay. So you know this decay is happening by emitting gamma rays mainly. So this radiogenic decay reaction cause some heat dissipation. Okay, so this is the heat actually mostly produced in the Earth's crust throughout this 4.5 billion years time. So we have a lot of heat inside the Earth. Most of them are due to the radiogenic decay. So at the original time of formation of the Earth, we call accretion of the Earth. At that time, the heat also dissipated. That is what we call the accretion heat. But Earth was formed from a magma ocean and a very hot body at that time, and gradually this accretion heat was reducing as a result of cooling, because any object that was heated will be subjected to lose heat gradually. So that means it is getting cooled with time. But in that case, if there is no extra heat available, our Earth should be very cold by now. This is 4.56 billion years now. But it is not the case now, because when you go inside to the Earth's interior, Earth is very hot still, right? If the accretion heat was the only heat source available, the Earth should be colder than what we experience now. But it is not like that. The reason is this radiogenic decay. There are a lot of radiogenic elements available within the Earth's crust, a huge amount, some tons of kilograms of material is there. The main three elements are uranium, thorium, and potassium. Okay, these are the heat producing elements. We call them heat producing elements. So these heat producing elements, they have decay constants in half lives in some billions of years. Okay, so therefore still they are not consumed, they are not finished, they are still there. Only some limited amount has been consumed as a result of this radiogenic decay, and now still we are getting heat accumulated due to this process. Okay, so remember, uranium, thorium, and potassium are the main contributing elements for this radiogenic decay. This radiogenic decay has been useful since many years before. In the history, people have started formulating some principles to calculate the ages of rocks mainly, right? For very recent things like archaeological things, we don't use these radiogenic decay equations because the half-life is very long for potassium, uranium, and thorium. That's why we are using some other aspects for archaeological things, because these archaeological things are not very old. Although for the average people it is old, but for geologists it's not old, right? 50,000 years means very short time, very young, very little age. Since we are talking about millions of years, right? 550 million years, for example, our metamorphic rocks, right? Even we call our Tabbo. Yeah. Don't you hear me? Yes, please go ahead.
The slides are not moving.
I am not moving the slides yet. I haven't started moving. Okay. I haven't started moving. I'm just explaining the principle yet still. Okay. Good. You are in touch with me now. Okay. Yeah, like that, give me the feedback whenever you have a concern. Okay. So even the sediments that we have in the northeast and the extreme north, we know they are Miocene times, right? It's very young. We call very young, even though it is 30 million years of age, right? So anyway, for long history, we are using this potassium, thorium, and uranium isotopes and isotopic decay equations to determine the time. So this is how we apply geochronological principles to rocks. So we will see how these isotopic systematics are used for age dating. And in addition to this uranium, thorium, and lead, we are using some other radiogenic equations. For example, the decay of rubidium and strontium, right? Neodymium, samarium, and neodymium, like methods, right? They are not producing heat actually, but they decay. They produce heat, but not that much. We don't get much accumulated in the as the crustal heat source. That's why we just consider heat producing elements as uranium, thorium, and potassium, right? But there are so
Excuse me,
many.
sir.
Yeah.
Excuse me, sir. Sir,
Yes.
Bhatia.
Yes,
Sir,
Bhati.
sir, අපිට පොඩ්ඩක් ඇහෙනවා මදි සර් මෙතන මේ සර්ගේ මයික් එක පොඩ්ඩක්.
ඇයි දන්නේ නැහැ නේ පොඩ්ඩක් ඉන්න බලන්න නේ. Just a minute.
හැබැයි